Hi, welcome back. This is Professor Ridge. In today's lesson, in section 4.4, theorems about zeros of polynomial functions. So we start off with the fundamental theorem of algebra. Every polynomial function of degree n, where n is greater than or equal to 1, has at least one zero in the set of complex numbers. So that's keyed in up there. We got we're using complex numbers. So every polynomial function, if you set it equal to 0, you can find at least one solution to that equation. So every polynomial function has one. And we can take this further and actually find n zeros of the function. So that implies that every polynomial function f of degree n with n greater than 1 can be factored into n linear factors. And again, not necessarily unique because you can have multiplicity. So another way to say this, we can write it f of x is equal to a sub n times x minus c1 times x minus c2 dot 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 x minus cn. So you're going to have n linear factors, linear being x to the first power minus some constant. Okay, and then c1, c2, c3 up to cn will be the zeros of the function. And also we can work backwards. I can give you the zeros and then we can work backwards to find the polynomial. So in this example, find a polynomial function of degree 3 with the given zeros. So again, if we're working backwards, if negative 3 is a 0, then we know that the function is going to be equal to x minus a minus 3, which is x plus 3. Remember, you change the sign. X minus 1. And if 4 is 0, then the factor is x minus 4. And if we multiply this out, we will get the polynomial. So we're going to FOIL. So we get x squared minus 1x plus 3x is plus 2x minus 3. Now we've got to multiply that with the x minus 4. So we're going to get x cubed minus 4x squared. So again, I'm going to take each term and distribute it, each term in the first parentheses. So now I go to 2x times x. 2x times negative 4. Now I'm going to distribute the negative 3. So I get negative 3x, positive 12. Combine my like terms. So we get x cubed minus 2x squared minus 11x plus 12. So that's our polynomial of degree 3 that has those zeros. Now, it could be, that's the easiest one. I can multiply it by any constant I want and, get a different function, but it'll still have those same zeros. So if I multiplied everything by 7, for instance, you can get 7x cubed minus 14x squared minus 77x plus 84. That will give you the same result, the same zeros, but don't make it hard on yourself. Just get the easiest one. Just make the a sub n, the constant out in front, make it 1. Let's try another one. So this one, we're going to get x plus 5, and then x minus square root of 3, and x minus a minus square root of 3, so that's plus square root of 3. And I would multiply these two first because that gives you the difference of squares. So that's going to be x squared minus square root of 3 squared, which is 3. And now this FOIL. So we get x cubed minus 3x plus 5x squared minus 15. And let's write it in descending order. That's not technically required, it's just nice. And that's our function. Oops. Okay, so irrational zeros. We have this property that if you have a plus c square root of b, where a, b, and c are rational numbers, and b is not a perfect square, then so if a plus c square root of b is a zero of a polynomial function f of x with rational coefficients, then its conjugate a minus c square root of b is also 0. So for example, so basically we're saying that solutions come in, or zeros come in conjugate pairs. So if I have 5 plus 3 square root of 2 is a 0 of f of x with all the qualifiers up there, rational coefficients, all that stuff. Then so is, but automatically I know 5 minus 3 square root of 2. And the reason that's true is because if you think about the quadratic formula, when we work it out, you get the opposite of b plus or minus square root of b squared minus 4ac all over 2a. So that plus minus gives you the conjugate pairs. Okay, so irrational zeros occur in conjugate pairs. Also, we're going to include the imaginary complex, in the complex forms. All right, let's try an example. So if we get negative square root of 2, now since we get negative square root of 2, we get automatically square root of 2 plus the square root of 2. So this is 0 minus square root of 2, 0 plus square root of 2. Okay, so we're going to get x plus minus a minus is plus square root of 2 times x minus square root of 2 times x plus 1 times x minus 4/5. Now to make our life easier, we can multiply any constant we want out in front of this, and I'm going to multiply by 4 to get rid of this. I'm going to multiply by 4 out in front to get rid of that fraction, and I'm going to distribute it into that parenthesis. So let's do these two. That's going to get us x, it's a different squares. So x squared minus square root of 2 squared is minus 2. Then I got the x plus 1, and then I'm going to distribute that 4 to the last parenthesis. Because multiplication is commutative and associative, so I can multiply it into any one of the parentheses. Not all of them, just one of them. So 4 with the last one is 4x minus, well, actually I need to do it with 5. I'm going to cancel the fraction. So that's going to be 5x minus 4. Okay? So let's distribute the last two. We'll FOIL it because we can kind of do that in our head. So 5x squared minus 4x plus 5x is plus x minus 4. Now distribute the x squared minus 2. So we get 5x to the 4th plus x to the 3rd minus 4x squared. Now distribute the negative 2. Negative 10x squared, negative 2x, and negative 2 times negative 4 is positive 8. Okay, so again, I'm just distributing the x squared to all three terms and then the negative 2 to all three terms. Combine like terms, and we get 5x to the 4th. Let's see, plus x cubed minus 14x squared minus 2x plus 8. And that is our polynomial with rational coefficients, 4th degree polynomial with rational coefficients that have the given zeros. Okay, so on this one, we're going to get the x minus, now remember this is in parentheses, so you distribute it, so it'll be x minus 6 plus 5i, and then you get the conjugate, so it'll be x minus 6 minus 5i, and then the x minus a minus 1 plus 7. So look, I'm not going to write this down both times. It's minus 1 plus square root of 7. You distribute the minus sign, so you get plus 1 minus square root of 7. And then the conjugate is x plus 1, So you can say it's going to be x minus a minus 1 minus square root of 7. So that would be x plus 1 plus square root of 7. Now, to do this, you got to think of the differences, the square of a binomial. So if I have, let me see if I can squeeze up here. Nope. If you remember, the square of a binomial is a squared plus 2ab plus b squared. I'm going to use that here and think of the x minus 6 as a, and the 5i is b. Oh, actually, I want to think of this one too. X plus b, difference of squares. X minus b is equal to a squared minus b squared. So I'm going to use both these formulas and make this problem a lot easier. So I'm going to use the bottom one, x minus 6, think of that as a. So I'm going to get the a squared minus the b squared, 5i squared. Okay? And I'm going to do the same trick in the second set of parentheses, or the last two set of parentheses. A is going to be the x plus 1, and b is going to be the square root of 7. So what we get is, now I'm going to use the square formula for x minus 6. So I'm going to get x squared minus 12x plus 36. 5i squared is 25i squared, which the i squared becomes negative 1, so we're going to get plus 25. Hopefully you followed that. And then for the second bracket, I'm going to have x plus 1 squared is x squared plus 2x plus 1 minus square root of 7 squared is 7. So now we got x squared minus 12x plus 61 and x squared plus 2x minus 6. And then I'm going to do the, I'm going to run out of room here, so well, I'll go ahead and do it. I'm going to distribute the x squared, so x to the 4th plus 2x cubed minus 6x squared. Distribute the minus 12, so minus 12x cubed minus 24x squared and plus 72x. Now distribute the 61, so that's 61x squared plus 122x minus 366. Combine like terms. X to the 4th, and then x cubed, we got 2 minus 12 minus 10x cubed, then x squared, we got minus 6x squared minus 24x squared, that's minus 30, plus 61x squared, so that is plus 31x squared. So now we got to do x's, so we got 72 plus 122, that's 194. And then minus 366. Okay, so that's the 4th degree polynomial that has those given zeros. So you get the two that were given to us, and then you get the conjugates, because we know automatically that irrational solutions come in conjugate pairs. Same with imaginary. Imaginary solutions come in conjugate pairs. Okay, so if we know a polynomial has a given a zero, so we're given that this polynomial, x fourth minus 5x third plus 7x squared minus 5x plus 6, has a zero of negative I, So if we plugged in negative I into this function, we would get 0. We know automatically they come in conjugate pairs. So what I do is I'm going to multiply x minus I and x plus I, or x plus I and x minus I together, and that's going to give me x squared minus I squared, which becomes plus 1. Okay? So now what I do is, now I know that x squared plus 1 is a factor. Since this is a factor, that's a factor. Because if it's a 0, then you do x minus the 0 to get the factor. And if I multiply those together, that's also a factor. So what I do is I'm going to take long division, x to the 4th minus 5x cubed plus 7x squared minus 5x plus 6. Divide out x squared plus 1. So x to the 4th divided by x squared is x squared. Subtract. So I got to distribute the minus sign. So minus 5x cubed plus 6x squared, because it's 7x squared minus x squared. Bring down the next term. Now x squared divided by, or the first term inside, negative 5x cubed divided by x squared, negative 5x. So we get negative 5x cubed plus, or minus 5x. Well, that's nice. And when we subtract, you change both those signs, so it'll be 0, 0. We get the 6x squared. Bring down the last term. And we start over again, so we get plus 6. And then we're going to subtract the remainder of 0. So, as it should be, because we knew that it's a x squared plus 1 was a factor. So now we have f of x is equal to the x plus I, x minus I, x squared minus 5x plus 6, and then we can factor that because it's a quadratic polynomial. So we get x minus 3, factor 6, add to 5, so x minus 3, x minus 2. Okay, so we set all these equal to 0. Now to find the zeros, you set it equal to 0 and set each thing equal to 0. Each factor equal to 0. And then solve them. So x equals negative I. That's the one we were given. X equals I. That's one we knew for sure because if negative I is the solution, so is positive I. The conjugate. X equals 3, so that's a new one. And x equals 2. So now we have all 4 zeros. Negative I, 3, and 2. Okay, on to Descartes' rule of sign. Let P of x, so let P of x written in descending order be a polynomial function with real coefficients and a non-zero constant term. Okay, so if there's no constant term, you can factor out an x and then you use Descartes' rule of sign. Okay, so you have to have a non-zero constant term. The number of positive real zeros is either the same as the number of variations in sign of P of x, and we'll talk about this in a minute, variation sign, or less than that by a positive even number. So for instance, if you have 5 variations of sign of P of x, then that means that you can have 5 positive real zeros, or 3, or 1. So you just subtract 2, subtract 2, subtract 2, till you get to 1 or 0. Okay? And then the test to find negative real zeros is you put in p of negative x. That's the key, and it's the same idea. Okay, so let's do a couple examples so you can see what I'm talking about. All right, so let's look at an example. What does Descartes' rule of sign tell you about the number of positive real zeros and the number of negative real zeros? So for positive real zeros, we look at the variation of sign of just f of x. We just put in positive x, which is the function itself. So we're just looking at the sign plus, and it has to be in descending order. Actually, it could be descending or ascending. I didn't write that, but it doesn't matter. And if you have missing terms, you just ignore that. That's no big deal. So, I prefer to do it descending order. So we have positive, negative, positive, positive, negative, negative. And we're looking for flip-flops, right? So this, from here, that's a variation, one variation. And then from here, that variation, that's another one. So that's two. It's not. That's a variation. And that one's not. So you have three variations of sign. Three variations of sign. So that means 3, or you subtract 2, 1, positive real zeros. Okay? So that means if I found 3 positive real zeros, I would stop looking for positive ones because I know there's no more. Okay, so that gives me some information. Now for the negative real zeros, and again from the fundamental theorem of algebra, we know it has 1, and then by extension it's actually going to have 5 zeros. Some could be real, some could be imaginary, but we know it's going to have 5 complex zeros. Now we're talking about real zeros. So if now you put in negative x, and the shortcut is anything that is an odd power, that's going to change the sign of the original coefficient. So this is going to become negative 4x to the 5th. Anything that's an even power, when you take a negative x to the 4th power, it cancels the negative and you get the original sign of the coefficient. So it stays negative 3x to the 4th. X cubed, that one is odd power, so that negative is going to come out, change the sign of the coefficient. X squared, that's even, so it leaves it alone, because negative x times negative x is positive x squared. Negative 7, that'd be plus 7x, and minus 3. Okay, so we're looking at the signs, minus, 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 plus, plus, minus. So no variation, no variation. Okay, there's 1, no, there's 2. So it's 2 variations of sign. Of f of negative x. So that tells me there's 2 or 0 negative real zeros. Okay? So our possible outcomes, so we have a total of 5 zeros, right? Whether they're complex, because it's degree 5. So if we have positive, you can have 3 positive, 2 negative, and that would leave you positive, negative, and then imaginary. Positive real, negative real, and then imaginary. So you can have 3, 2, and 0 for a total of 5. Or you can have 3, 0, 2, again for a total of 5. And then we can have 1, 2. Now again, you have to have 5, so if you have one positive real, 2 negative real, that gives you 3, so that means you have to have 2 imaginary. So that's for a total of 5. You always get a total of 5. And then the other combination, you get 1 positive real, 0 negative real, and then 4 imaginary. Okay, so that's all the combinations from Descartes' rule of sign. Okay, let's move on to the rational. Actually, let me do it on the next page. Okay, so the rational zero theorem says let p of x, polynomial function, right, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 1 x plus a sub 0, where all the coefficients are integers. So that's a key qualification there. So all the coefficients are integers. Consider a rational number denoted p over q, where p and q are relatively prime, meaning it has no common factors. If p over q is a 0 of p of x, then p is a factor of a sub 0 and q is a factor of a sub n. So this theorem is a great theorem, actually. It helps us search for zeros of a function instead of shooting blindly in the dark to find out what is a zero, right? So basically all we could do up to now is we just guess and plug it in and see if it makes a zero or not. And then you know, if you can't factor this, you have to find something that works. So you guess and check until you find something. Well, this theorem is telling us where to start looking. If something is a zero, if a rational number, if a zero is a rational number, the only way that it's going to be, it has to be a factor of 4 over 3. Okay, so the possible rational zeros are, so you're going to do a sub 0 is 4. We can ignore the negative, so the factors of that, p could be, p could be 1, 2, and 4, and then we can do positive and negative. And then a sub n, which in this case is 4, is 3, and so that's going to be our q, the bottom number, and the factors of q are, I should put colons here, equals, right? So q could be 1 or 3. So our possible rational zeros are p over q, where p could be 1, 2, and 4, and q could be 1 and 3. And you do plus and minus. So p over q could be plus or minus. We're going to do p 1 over 1, 2 over 1, 4 over 1, and now we're going to do each of those over 3. So we can do 1 over 3, 2 over 3, and 4 over 3. And they can all be plus minus. I just put a big plus minus out in front, but right, the idea is all of these could be. So there's only 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 possibilities times 2, the plus minus. So there's 12 rational numbers that are possible that work. Okay? So I don't have to check any other ones, just those 12. So now I'm not shooting blindly in the dark. So if I want to find some rational zeros in it, I'm going to start with those. I'm going to start with 1, 2, 4, and so on. If none of those work, then they're not any rational zeros. They're going to be, you can get irrational or complex, imaginary. Okay, so again, find only the rational zeros of the function. So what's nice about this rational zero theorem is I know that P over Q could be factors of 10. P could be 1, 2, 5, 10. Q could be factors of the leading coefficient is 1. So that makes it really easy for me. Plus or minus 1, 2, 5, or 10 over 1. So I only have to try these 8, the 4 plus or minus, so that'll be 8 possibilities. So we're going to try, let's start with 1. So descending order, we're going to do the synthetic division. So 1, negative 2, 1 times negative 2 is negative 2, and that's not going to work. So 1 doesn't work. Now we're going to try, let's try negative 1. So we're going to get 1, negative 1, positive 4, negative 5, 2, negative 12, which is not 0. So 1 and negative 1 don't work, so that one's no good. So now we'll try 2 and negative 2. 2, 1, negative 3, negative 9, 3, negative 10, negative 2, negative 22, negative 50. So that one doesn't work. So now let's try negative 2. So 1, negative 2, 10, negative 2, 10. Oh, that one works. Hooray! And finally, after 4 tries, right, there's only 8 possibilities. So negative 2 works. And just to save time, I'm going to, we'll just go to 5. 1, 2, just go in order there. So 5, 1, negative 3, negative 9, negative 3, negative 10. So we're going to try all 8 of these. Oops, that should be 1, 5, 2, 10, 1, 5, 2, 10. Oh, there's another one. Okay, so now we got 2 and negative 2 and 5. Then you can try negative 5. I'll let you try on your own. You can try negative 5, it doesn't work. 10 doesn't work. Negative 10 doesn't work. So we just get those 2. So negative 5 doesn't work. 10 doesn't work. And negative 10 doesn't work. Okay, so on this problem we just want to go through the whole list and check them. Or what I would do is actually factor it out and continue to factor there. Alright, so that the Rational zeros are -2 and 5. Okay, so let's put it all together and factor f of x into linear factors and then find all the zeros of the function. So I'm going to use Descartes' rule of sign. I know my possible rational solutions are or zeros, I should say. Solutions, meaning when I set it equal to 0. So possible rational zeros are going to be, we got a sub zeros 4, -4. Again, I just ignore the sign. 1, 2, and 4. A sub n, which is 4 in this case, is 5. So that's going to give me 1 and 5. So my possible rational P over Q is going to be 1 over 1, 2 over 1, 4 over 1, and then I'm going to put them all over 5. 1 over 5, 2 over 5, 4 over 5. And then you have the plus minus for all of them. Okay? So that's where we're going to start. I can do Descartes' rule of sign and know that I got 1, 2, if I count rule of sign, so we got plus, minus, minus, so there's 1, 2, 3. So 3 or 1 positive, real. Now, it's real doesn't mean that it's going to be rational, right? Because we can get 1 plus square root of 5. That's a real, positive, real solution, but it's not rational. So, be careful. And then if we do f of negative x, remember, only the signs that are going to change are the odd ones. So I got 5x to the 4th, so that will stay positive. Negative 4x to the 3rd, so that will change to positive. Then the x squared stays the same. The x changes. And so we only have one variation of sign. See, there's no, no, no. So we have 1 negative real. And again, I don't know if it's rational or irrational, but I know I get 1 negative real one. So that might be a good place. Okay, so I always start with 1, and normally what I do is I just plug 1 in to see if it gets a 0 first. So it's 5 minus 4. So I'm just kind of showing you the way I do it. And I don't write this down because the ones just go, the ones to the any power is just 1 times the number. So you just do the coefficients. So it's 5 minus 4 plus 19 minus 16 minus 4. Punch that in your calculator. So 5 minus 4 plus 19, 16 minus 4 is 0. So that works. So that tells me that 1 is a 0, so I'm going to do the long division, the synthetic division. It's only a waste of time when it works. When it doesn't work, just plugging it in, it's real quick. You can check, does it work? And then you can cross 1 off your list there and go to the next number. So nice that it works, because that gives us 1. So we're going to go 5, 5, 1, 1, 20, 20, 4, 0. So now we have f of x is x minus 1 times this polynomial is left over, 5x cubed plus x squared plus 20x plus 4. And we're going to factor that one. So what I do is I just start here again, and I'm going to check 1 again. to see if 1 works. 5 plus 1 is 6 plus 20. Okay, so 1's not going to work. And if I look at variation in sign of this one, there's no more positive ones, right, because there's no variation in sign. See if we look at variations. So that tells me that there's no more positive ones, so I'm only going to check negative ones now. So I'm going to try negative 1. I'm going to use the polynomial that was left over. Sometimes we refer to that as the depressed polynomial. So 5. Negative 1 times negative 4 is 4. 24. Okay, it's not going to work, right? So I don't really care what that number is. It just doesn't work. So now I'm going to try, what's my other possibility? 2. So let's try 2. Oh, and I already know positive is not going to work, so I'm going to do negative 2. 5, 1, 24. Negative 10. Negative 18. Negative 4, 0. See? So that helped me, right? I didn't have to do positive 2 because I already looked at the variation. All right, so now we know negative 2 works. So now our polynomial is f of x is the x minus 1, the x minus a minus 2, which is x plus 2, and then 5x squared minus 9x plus 2, and we can use factors of 10 that add to 9. Okay, there aren't any. So I have to use the quadratic formula. So if you use quadratic formula to solve this equation, those are going to be your zeros, and then you just do x minus each of them for the factors. So opposite b plus or minus square root b squared minus 4ac all over 2a. So punch that in your calculator. So there'll be 9 plus or minus square root of b squared minus 4 times 5 times 2 is 40 all over 2a, which is 10. So that'll be 9 plus or minus, and see the plus or minus, that's where you get the conjugates. So this will be, hang on. Alright, so a nice teachable moment here. I was just wondering, looking back at my work here, negative 9 times negative 2 is positive 18. So the negative 2 doesn't work. So we need to scratch this. Alright. You know, sometimes something catches my eye and it's like, oh, I better check that. Okay, so let's see, negative 2 doesn't work. Let's try, what would be the next one here? Negative 4. So negative 4. So we got 5, 1, 20, and 4. So that'd be 5, negative 20. Okay, and that's going to be a big positive. 76, 90. Okay, so it's not going to work. Okay, so that one doesn't work. So now let's try negative. Again, I don't have to try positive, so I'm going to try negative 1/5. So negative 1/5. And I got 5, 1, 20, 4. So that's 5, negative 1, 20, negative 4. Ah, nice. Okay, so now f of x is the x minus 1, x minus a minus 1/5, so that's plus 1/5. And then we got 5x squared minus, or plus 20. Now that one's easy to factor, right? Because you can factor out the 5. And move it to this other one, or just bring it out to the front, it doesn't matter. So normally I would put it in with this one here, the x plus 1/5. So we get x squared plus 4. And then that's easy to factor, because if you think of it as the difference of squares, you get the x plus 2i and x minus 2i. So when you do that, multiply that, you get minus 4i squared, which becomes the plus 4. Okay? So that's factored form. Now we want to find the zeros. Just set all those zeros. So the zeros are 1, negative 1/5, negative 2i, and 2i. Alright, so that concludes the lesson for 4.4. Go to my math lab and complete your exercise there. See you next time.